Okay, so welcome everyone to this IVM seminar today. We have, as a speaker, we have Joshua Telser from Roosevelt University in Chicago area, and a little bit about Josh. So Josh studied at Cornell and then moved to Florida for his PhD in inorganic chemistry. And then he did a postdoc with Brian Hoffman at Northwestern, still in Illinois. And then he did a brief stint in companies before joining again the University of Chicago. And then he moved to Roosevelt, where he's still nowadays. A little bit about his research. So Josh dedicated most of his research endeavor to inorganic chemistry of transition metal using EPR spectroscopy as especially at high magnetic field as his technique, spectroscopic technique of choice. And today he's going to tell us about his studies on iron 2 scorpionate complexes. So Josh, the floor is yours.
We're okay. Thanks a lot, Thomas, for this opportunity. I apologize for being a little late. I see there's some people in Germany, so it's pretty late for them. It's 8 in the morning for me, and may not sound super early, but it's kind of tough getting here exactly by 8. So as Thomas said, yeah, we've been looking at scorpionate complexes for a pretty long time now, and I really like them. So do a lot of people. If you look in the Cambridge Structural Database, I don't know how many thousands of structures, there are tens of thousands possibly of structures there are of this ligand platform, which I'll introduce in a moment. Okay, so everybody, I think, knows some of the people at the Magnet Lab, Jurek, Andrew, Mike Ozerov, for the far infrared, and mentioned that. Sam, I don't know who remembers Sam, who's still around, but Sam was a graduate student with Mike Shatruk and Steve Hill, I guess technically an FSU chemistry grad student, who's now at Los Alamos doing some pretty interesting work there. If anybody was at the Magna meeting back at the end of February, beginning of March. And Sebastian, so Musbauer expert, he was at the Magnet Lab for a while, and now he's at the University of Idaho. I think I put yeah, that's right. I never remember what I have animated. I put their current affiliations here as well. And this project was started with Klaus Teopold at the University of Delaware and his grad student, Dan Cummins, and it kind of stagnated for a while and then was resurrected by Adam Fiedler and his grad student Lakshmi at Marquette University. And Lakshmi, she was actually briefly in Florida at Florida Atlantic University, but now she has a job in industry in Oregon. And then I think there's some people who are familiar with these folks. So Dan Santalucia and Mikhail Atanasov. I guess technically it's both the chemical energy conversion and the Kohlenforschung, but I just put one of these logos, I think, or anyway. Okay, so Scorpionate. So this is taken from I think an article in Chemical Engineering News years ago, and the scorpionates were developed at DuPont, the chemical company that may or may not exist in any capacity anymore, and certainly not in the central research that existed back in the 50s or maybe even 1940s, 50s, 60s, 70s that was equivalent to a major chemistry department in terms of their productivity and basic research. Anyway, so it may have been the marketing know-how of a company such as DuPont that came up with some catchy kind of image like this with the scorpion, pretty nasty looking creature. I don't know if I've certainly never seen one in the wild. We don't have them in this part of the country, but in the Southwest, I suppose. So this is actually sort of a weird depiction of the scorpionate, but because it has an R group, which wouldn't really be something coordinating to a metal, but so be it. Anyway, it's kind of a nice picture. Here's the person who developed them, Sviatoslav, or Jerry, as he was known in this country where people can't really handle those kind of names, as I think Urek can give you firsthand experience on. So he was from a place that probably many people would not have heard of. Unfortunately, it's in the news a lot. When he was born in 1931, it was in Poland. Earlier, it was in Austria. Went through a Soviet period that I don't want to put on here, and is currently in Ukraine. But he was one of the refugees, the DPs, as a result of all the chaos from World War II and its aftermath. So this is a nice kind of obituary by his colleague John Burmeister at the University of Delaware, where he moved pretty close, since Delaware is the second smallest state in the United States. It's quite tiny, from DuPont, which is also in Delaware. So here's another Scorpionate picture of not, I don't know, sort of using the tail, whatever. And then I have a copy of this book, and there's this scorpion again. So they're pretty into that, obviously. So here's what they look like in a more normal chemistry type view. And this was started, or my involvement started with Pat DeRocher at the University of Central Arkansas, who is still working on these, but more for polymerization applications. So they're based on the pyrazole heterocycle. It's one of many nitrogen heterocycles. Pyridine, maybe everybody's heard of, that six-membered ring with one nitrogen. There's imidazole, which we'll see in a second. There's a whole slew of these, and many of them are part of biologically active molecules. Most drugs, in fact, have a nitrogen heterocycle in them in some capacity. And this nitrogen here, which is the 2 position, is the one that's the Lewis base. This one is not, because the lone pair on this nitrogen is involved in the pi system, making this an aromatic molecule, which is why in this depiction we have a little circle as opposed to the localized bonding. And this is the most popular one, the tris-pyrazolyl borate. So there's 3 of them, and they're held together by the boron. So these are formally, and in fact, in the original synthesis, derived from just, I guess, potassium tetrahydroborate, so KBH4, and then you can react it with pyrazole and make this. I think the original work has something to do with trying to make some kind of polymers, because that was really DuPont's thing. But it turned out that Trofimenko made these, and the rest is history, as they say. There's also a lot of interest in the bispyrazolyl borates, which are only bidentate ligands. And so we haven't looked at them too much, but that's another one. And that's in fact what was sort of shown in that figure with the scorpion. So there's quite a number of different geometries, and a very common one that I'm not going to discuss at all has been looked at a lot by Dave Tierney in the cobalt complexes at Miami University in Ohio, not the one in Florida, are the biscorpionates. So you just have 3 of the, or 2 of these ligands, 3 pyrazole donors to make a 6-coordinate complex. There's a group in Russia that's also looked at them, I think, with Alexander Schnegg, at least maybe in earlier times, using the terahertz EPR method. But what we're looking at exclusively are the 4-coordinate ones. So there's the scorpionate platform, as we call it, and then there's an ancillary ligand, and that is quite variable, and that's essentially what we've been kind of fooling around with over the past years. And then I don't think I'm going to get time to talk about this, but I've had a very productive relationship with Jeremy Smith, who started his independent career at New Mexico State University out in the far southwest of the US, and then has moved up in the world, I think it's fair to say, to Indiana University, up north and prestige-wise, and closer to me, although not that I really see him very much, at Indiana University in Bloomington. And so these are based not on pyrazole, but on another very common, popular nitrogen-containing heterocycle, and that's imidazole, and anybody in the bioinorganic chemistry area knows about imidazole because that's the side chain of histidine, one of the most, maybe the most popular metalloligand in biochemistry, and that's coordinating to metals through this nitrogen that I'm pointing at here, which would be in the 3 position. But what these new style, as I call them, scorpionates, are ones in which this hydrogen, it's not shown in this line drawing, but this hydrogen has been removed, and you formally end up with a carbon donor or a carbene. And there's just been a huge amount of interest in these. This ChemRev is already a few years old now, but it has, as an example, whenever I made this slide, which is a sort of old slide, had 472 citations and now 711, and it's just sort of a random NHC review article. They're used a lot in main group chemistry. It's just a huge area now, and often those are simply monodentate, which I'm not talking about at all. But the version that Jeremy has used a lot is the real scorpionate analog, and that's with the the trisimidazolyl borate that's shown right here, but it's a 3-carbon donor rather than 3 nitrogen. The nitrogens are there, but they're not involved directly in bonding. And then you can do the same sort of changes in the L or X, whatever you want to call it, ligand. And we've also looked at some of the 6-coordinate ones that are analogous to the 6-coordinate tris-parazolyl compounds that I've talked about. And there also are the bis imidazolyl. Here you can see the little carbene carbon depiction. And, there's no good kind of freshman chemistry way of drawing it. So we have a variety of ways of drawing that, but it's a pretty strong donor, and it's interesting to compare these properties with those of the traditional parazolyl compounds. Okay, so this is a series of these kind of compounds. These are all with the tris-parazolyl that's shown across here with the different metals and more or less the same ancillary ligands or substituents. Ancillary ligands, that's, I guess, this one, the substituents on the pyrazole. And just sort of one aspect about the inorganic chemistry, which is that you need in general to have a bulky group right here. And that's at the 3 position. This is the 3 position. This is the 5 position down here, which just for synthetic reasons often ends up getting some kind of substituent, but that's not a particularly important one. It's not unimportant, but not particularly important, whereas the 3 position that I don't have a space filling model, but that's really pointed, out in this direction is crucial to prevent the 6-coordinate complexes, which are nice in their own right, as I said, but not what we want here. So we have the steric bulk here that kind of protects this position. And, you could kind of call that biomimetic, as like modeling what a protein might do if you really want to, get carried away with it. Surprisingly, though, it is still possible with just the methyl group here, and these were the original complexes from Pat DeRocher, that it was possible to not to have the 6-coordinate complexes, but it's a lot better to have a T-butyl or a phenyl. And a popular one with Jeremy Smith is the adamantyl, which I don't show, and it's a, if you're not familiar with organic chemistry, you probably don't know what adamantane looks like, but it's a very big blob of hydrocarbon that really provides a lot of steric hindrance, protecting this position. Okay, so these are arranged in order of the periodic table, which is not the order that we've looked at them. The first one that and I don't want to say the best, maybe I shouldn't, like it's been now downhill from there, but I think we were lucky in that, at least in terms of the high field EPR spectroscopy, back when we, or at least certainly I, was not as familiar with the whole concept, the nickel complexes from Pat DeRocher were the most successful. And I should also add that it led to some, I think, pretty groundbreaking work by Frank Nese and Chengfei Ye in terms of doing a study that now would be really routine that, even I could do with Orca, but at the time was, I think, pretty groundbreaking in terms of doing really serious electronic structure calculations, and it was using in part our data on these complexes. So we looked at 3 different halides: chloride, bromide, and iodide. Fluoride is not possible because you get a bridging fluoro, although if these had T-butyl, it might be possible to prevent that. So something one could go back to, but not too excited about that now. This is pretty much completed. This study here, and this was with actually with some complexes from Trofimenko himself before he passed away, and then later with Adam Fiedler, are a variety of cobalt-2 complexes. And so same general structure. In this case, with cobalt-2, it's possible to have the whole halide series. And this is with the T-butyl, so it's a little bit better design, ligand design. And so those are pretty much completed. And then this one is what I'm going to talk about today, that I think, God willing or whatever, is going to be completed maybe even this month, or at least let's say submitted this month, and that's on iron 2. So these are, I'm not going to push the bioinorganic aspect, but I mean, these are all important ions in metallobiochemistry. The first row transition metal ions are all, with the exception of chromium and titanium, have some role in biochemistry, and iron, of course, has a huge role, and even nickel and cobalt do as well. And cobalt is also useful as an analog for a spectroscopically active analog for zinc. Anyway, and then we've also moved, oops, where the heck, there we go, moved down in across here with copper. This one is spin 1/2, of course, and we can look at by regular EPR. It's maybe not as interesting as I had thought, and the structure is actually not really quite like what's shown here, but I mean, the connectivity is that, and it is possible to have the fluoride, chloride, and bromide, but in this case, not the iodide, because that is too electropositive, and you get a reduction of copper 2 to copper 1. So there's a ton of copper 1 complexes, which are boring and diamagnetic, just like the zinc 2, that are biologically relevant as models. And then what's also in progress, and hope to get the finalized data from the magnet lab pretty soon on this, is a series with nickel, but now with a little bit more interesting, I guess you could say, or certainly different ligand, and that's the phenyl chalcogenide. So the whole series of group 16, not group 17, so oxygen, sulfur, selenium, and tellurium. And so that's in progress. And those compounds are from Mike Jensen at Ohio University. And so these are just some of the techniques here. I put, obviously, the high field EPR isn't really needed for copper. Okay, so one of the big things about this is the spin orbit coupling, in terms of, what people in the molecular magnetism area make a big deal about this sort of thing, in terms of getting the serial field splitting that can lead to single molecule magnet behavior. And I'm certainly not the expert to talk about that, but one of the topics which Kim Dunbar and others have looked at is to try and say, well, what happens if we go to heavier elements? We have Murik and I are working on that with Mike Rose at the other Texas school, University of Texas, Kim Dunbar at Texas A&M, of course, and to try and see what happens as one moves down in the periodic table, which of course is what we're talking about in going from fluoride, chloride, bromide, or from oxygen, sulfur, selenium, etc. So here's a picture. This is from one of my favorite databases, which is under threat. I heard they were going to get rid of it. We don't need to get into all that disaster now, but maybe it'll be maintained. In any case, it's a really cool database with atomic spectra, as you can see from here. And so one can pull out various parameters. And so this is just showing the group 18, which we don't make compounds of, but these are the monocations. So this is all the NP5 configuration, and you can just see how the spin orbit coupling, this is the single ion or atom in the case of the halogens, spin orbit coupling goes up. And, in terms of fluoride and chloride, and this is something that we found in our work, particularly with cobalt and also here with iron, that the spin orbit coupling doesn't change very much going from period 2 to period 3, but because of other factors involving just sort of more plain old chemistry, there is a big difference between fluoride and chloride, but it has nothing to do with this relativistic effect, if you want to call it that. But when you start getting down in the periodic table, and you get a similar plot for the chalcogens as well, don't have that data easily available, you get a huge increase. And this, of course, is the same sort of thing that happens in the D block. So if you're talking about osmium or iridium, it's just a huge effect, the spin orbit coupling, as opposed to in cobalt or iron. And this is, of course, also very relevant compared to, or when we're talking about the F elements as well, which we're not getting into here, but it's a huge area. Okay, so anyway, finally, then here's the series that we're interested in, the complete group 17, so fluoride, chloride, bromide, and iodide. Here's the structure. I mentioned this about the T-butyl group in the 3 position, and actually the bis scorpionate iron complexes where there can be, oh, my dentist is calling, where there are a variety of substituents here is very interesting in terms of spin crossover behavior. So going from high spin to low spin, I think both in the iron 2 and iron 3, but that's not something we're getting into, although it's been studied a lot. So this was reported a while ago, I guess 14 years now, geez, by Klaus Theopold at the University of Delaware in this paper given here. And they got structures for the whole series. The fluoride synthesis was, if I may say, kind of a little shaky. Say something about that later. But they didn't, Klaus Theopold is a synthetic chemist. They did, some characterization, but they didn't do all the fancy spectroscopy. They didn't do any Mossbauer, and certainly not any kind of fancy EPR, which these are all high spin iron 2, so that wouldn't really come to mind anyway. Yeah. And so then we got, meaning Sergey Lindemann, who's the crystallographer, now retired from Marquette. They have a new one there. And Lakshmi got crystal structures of the whole series of these. And they're a little bit different. One of the aspects of coordination in chemistry is that it's almost as though if one gets, n attempts to make crystal structures, get crystal structures, you have maybe n-1 different results. I mean, they're not a big difference, but they're pretty sensitive, these kind of compounds, to crystal packing or who knows what. And these are all neutral compounds too, I should add, because we have a -1 ligand and then we have -1 ligand up here. They're all iron 2. So it's not from, any counter ion, which is another huge complication. So that's just the way it is. And in contrast to some of what we've done on tetrahedral paramagnetic complexes, where the optical spectrum is very informative, it's not really that's not the case here. These are all colorless compounds, which is kind of boring. The fluoride compound was really not a very successful conversion, but then Lakshmi was using thallium fluoride, which thallium salts are bad news, but she knew what she was doing, and no ill effects from that. And thallium is very good for a lot of the thallium cyclopentadienide is a really good reagent, and just kind of the way it goes. But anyway, so I was able to make the fluoride compound more successfully. So here's some of the visible, or I'm sorry, near IR spectra. The visible spectra down here are nothing, but there is one band which has 2 parts to it, as you can see, or I guess you could say 2 bands in the optical spectrum. This spike here is from solvent. That's a vibrational hot band. But there's this big broad signal right here, and you can see some of the trends that one normally thinks of in transition metal chemistry, the spectrochemical series where the splitting is larger for chloride than for bromide and then for iodide. As just another view of the same thing. This was done by Dan Santalucia, I think. Yeah. Oops, I'm sorry. And with more fancy deconvolution to get the band positions somewhat better. And so that's what we're using to try and fit them. And the actual symmetry is not C3V, but it's CS, and that's what we think the splitting here is coming from. But for the ligand field analysis, you can just forget about that and just do a qualitative or semi-quantitative study using the trigonal symmetry, ideal symmetry. So in the Milheim, they have really good Nussbauer facilities, thanks really to the late Eckerd Bill. And so Dan got Nussbauer spectra for all these. I'm not an expert on describing these, and some of them show more than one species, which we're also seeing in the EPR. But the zero field Nussbauer parameters are pretty typical for high spin iron 2, no surprise. As I said, that had not been reported before, although, in principle, in principle, zero field Nussbauer probably could have been available to the Theobald group, but wasn't that big of a deal. Here's just another one. I didn't fit it all in the same thing. So it's, the important thing, however, as the applied field. And so this is what they can do in Milheim, and Sebastian Soyan at University of Idaho, I guess, can do this now. Closer to Tallahassee, Caitlin Meyer at the University of Miami, I think, is getting her applied field Nussbauer set up going. And then at Carnegie Mellon in the US also, there's applied field Nussbauer, Alex Guo, that studies a lot of metalloprotein, metalloenzyme complexes, but there's not a lot of it available out there, and it's much more informative and much more complicated because of the hyperfine effect that's revealed with the applied field. And I'm not, any kind of expert on this. Here they're using kilogauss, so 70 kilogauss or 7 Tesla. Not sure why they're using kilogauss. That's okay. We're all Tesla at the magnet lab now. Nothing to do with Elon Musk, I don't think. Anyway, so it's possible to get all kinds of information from that, in particular, the zero field splitting that can be then compared to what we get, I'll dare say more effectively from the magnetic resonance techniques. Okay, so here's, I think these are the latest numbers for these. And in addition to the Nussbauer studies, Dan also did regular old magnetic susceptibility, which is something that, how should I put it? Well, I just saw Urek sign in. I don't want to get him into trouble by quoting him, because he had a rather, let's say, unflattering quote about magnetic susceptibility. Let's say it gives you data and you can fit it, and oftentimes people are happy with that. So here we are. So these fits to the DC susceptibility give you G values, the full set of spin Hamiltonian parameters, the G values, the zero field splitting here. This is the E over D rather than the E value. And it's kind of surprising to me, based on this, that the zero field splitting rhombicity, the E over D, is really large for something that you think of as being ideally trigonally symmetric, so that the X and Y directions, with the Z or Z direction being along the halogen axis, should be the same, but they're not. So that's kind of surprising from this. And then this is just an energy level diagram showing what sort of things are going on in terms of this is really for EPR kinds of transitions. Okay, so here's an EPR spectrum. This is a figure that Dan made using a color scheme we're not really too clear on. But anyway, this is, and I don't know if the y-axis is really that realistic nomenclature, but anyway, so this is at 208 gigahertz at 6K, so kind of standard conditions in Tallahassee. And this is the bromide complex, which shows two species, which I believe is what also the Nussbauer showed. And then more fancy plots here, or diagrams. So this is from Mike Ozerov, I think, un massaged through Milheim, so straight from Tallahassee here, the heat plots, and I just point some of the transitions. I think these figures actually look pretty nice, if I say so myself, and I had nothing to do with it because it's all Mike's work, but you can see the blue here, that's the strong kind of transition, and you can see the field dependence. The field is given on the y-axis. The white spaces are places where there's just basically no power from the far infrared source, and some kind of complication, but you can see these patterns. And, I kind of like this because you're unbiased. I mean, you can really see the field dependence of these transitions without having a bunch of fit lines on them that kind of force you to say, yeah, oh, that's what it is because I see the lines. But this is the real, unvarnished data. So here's the EPR parameters. The ones in italics were taken from I think from the magnetic susceptibility. And I should add, you might say, oh, that's not such a great thing to do, but the G values are really uninteresting. One of the take-home messages I just want to get across is that in contrast to, say, EPR of a spin 1/2 system, where essentially all the information or the bulk of the information is in the G values, here the G values are just sort of like, yeah, okay, that's what they are. It's high spin iron 2. They're something over 2, like 2.2 plus or minus 0.1. And who cares? You can make a big fuss about them, but they're really not very interesting, and they're pretty much the same as all kinds of other high spin iron compounds, high spin iron 2 compounds. So quite uninformative, and in fact, pretty much the same as what you get for the intrinsic G values of cobalt 2, nickel 2. They're all greater than half filled. They're all like in the 2.2 range, so nothing very exciting. And whether you fuss over whether it's 2.306 or 2.3081, who cares? Anyway, but what is important is the zero field splitting parameters that I think are pretty accurately and quite precisely. I mean, 10, I did a little rounding here, in fact, from the precision that was the table I took this from. But anyway, quite good precision and presumably accuracy as well. And what you can see from this is I don't have the nickel values, but the nickel values showed a nice trend of magnitude, well, not magnitude, even magnitude and direction, going from down the periodic table. And that's not the case here, because we go from a large magnitude negative to pretty large magnitude positive to pretty close magnitude positive, and then zoom back down to a large magnitude negative. So this, doesn't look anything like the nice graph that I showed of the spin orbit coupling constant. So it's a much more complicated effect than that. Excuse me. The other thing that's interesting, of course, is that the fluoride complex, as you might expect, is fairly axial, and then the others are all extremely rhombic, which is in agreement with the magnetic susceptibility. So that's kind of gratifying. And then I can do my own EPR, such as it is. This is at Northwestern University in Brian Hoffman's lab. And this is just using a regular old, well, they have all kinds of fancy EPR, but this is using the cheapest, most ordinary EPR spectrometer that's available there, regular old X-band. And as maybe some people know, maybe not everyone, there's sort of a myth that I think we're helping to dispel over the past years that, oh, integer spin species, yeah, they're paramagnetic, but it's impossible to get EPR. That's not true. It's possible even from S equals 1, and it's even more possible from the higher spin, integer spin, or non-Kramers systems. And it's been shown by Mike Hendrich and others, iron 2 is actually relatively feasible for conventional EPR. They use, as I say, Hendrich uses a lot of parallel mode detection. This is not parallel mode detection. This is just absolutely ordinary perpendicular mode, a very routine EPR. This is actually at 4K. I don't remember if this showed anything at liquid nitrogen now. But in any case, you get this big, strange looking signal here. These are just two different preparations. And, there's some variability because, as you can imagine with this signal, that's this weirdly shaped, the tuning and the free, the glassing and all sorts of stuff. And it is a different actual species, in terms of preparation, it's pretty much the same. I wouldn't make a big deal about these little wiggles. And there's a little bit of some junk that's in there that's a spin 1/2. I mean, it's tiny compared to this whole thing, and it doesn't really matter what it is. Anyway, so this is the fluoride complex, and it has the smallest E over D, and that's good for what we're talking about, because if we look at this energy level diagram, this is for a positive D value, but that isn't really too important. What we're looking at is a transition that's not shown by an arrow here, but it's between these two levels, the sort of so-called -2 and the +2, that in a rhombic field environment, those are not degenerate. They would be degenerate if it's axial, but when it's rhombic, they're split by a little bit. And in this case, that little bit corresponds to the microwave quantum of, frequency of 9.375 gigahertz in this particular case. And it works out. The problem with the other three, so these here, their E value is much too large. So it's just not possible. And it's too big even for the Q-band or 35 gigahertz EPR that we could try. And that's also a little tricky experimentally, which I won't get into. But anyway, it's a nice thing that you can see this. And in fact, it does give you some information on what the rhombicity is, because it's that E value that's generating this splitting that is observable at X band. So the lesson from this is, just try and get a regular EPR spectrum. Oh, okay, that's right, there it is. From something that's a spin 2, even if you might not see anything, but you still might. So this is a pretty massive and confusing looking slide, and I already kind of, my eyes glazing over even making this thing. But of course, you got to remember, this is from Wilhelm. As I said, ground zero for Orca, or Fragnese is, and the latest and greatest versions of Orca, which is a godsend to all of us wannabe, I won't say wannabe quantum chemists. I'm not even a wannabe, but at least people that can, run a DOS program, I guess. That's about it. Anyway, so here's the G values. Here's the D value and the rhombicity. And it's, I think, pretty impressive here, just looking that the rhombicity is really pretty large. I mean, I don't have, I'm sorry, I should have, highlighting was not too smart. But anyway, this is the ones with the compound name are the experimental. So we can see that in certain cases of optimization, we can get this high rhombicity. And so that to me is really quite gratifying, because from, as I said, a simple just coordination chemistry point of view, it doesn't seem that should be the case. And I'm not going to come up with a simple explanation for why it is, but it's, the fancy quantum chemistry does reproduce that. And then we can also take a look at the D values. Now, what I have here and what makes it complicated is that it turns out another take-home message is that you could use the crystal structure, which, as I said, are variable. There's the original Theopol structures, and then the Marquette structures that are presumably of the exact compounds that we were looking at spectroscopically. And then that's the H only. So that's essentially the crystal structure where they just did an optimization to get the hydrogen locations exactly right. So it's essentially nothing really. But then they have these two different kinds of optimizations. I think, I guess I forgot to put the one down for the fluoride. That's okay. The slide's bad enough. But anyway, there's another optimization that's what they call minus for the fluoride. But anyway, so this is your sort of optimization that you might do in general. And the point is, you can see that here, taking a look at the fluoride, for example, it's not an enormous difference. And you can say this one is a little low in magnitude, this one's a little high. What's right? I don't know. Both of these, to my mind, are acceptable in terms of reproducing the experiment about as well as one could hope, and similarly reproducing the small rhombicity. Uh, and in this case over here with the chloride, because of the presumed complete rhombicity, there's no meaning to the sign here. So if you feel better, we could put a negative sign here. But, in this case, this is a pretty poor agreement, and it's a little better with the optimized geometry. The chloride was tricky because it has or some forms have crystallographic threefold symmetry, in which case then the rhombicity would be 0. So that's a whole different story. That's probably not what we were looking at. And then over here with the bromide, this is pretty decent agreement, I would say, but the optimization is significantly worse than the crystal structure. So, go figure. And that's true also with respect to the rhombicity. And then lastly, with the iodide, this is kind of crazy. I had to make sure that this wasn't a typo, that here just using essentially the crystal structure is, really quite good agreement. We're off by maybe 15% or so, whatever. And then the full optimization is just completely wrong in terms of the sign. So whether that's something to do with having the heavy atom, so we're finally seeing in a kind of indirect way a heavy atom effect, at least computationally. I really don't know enough to say, but it is kind of surprising. And then lastly, there's this whole mass of G values, which maybe I should have just left out of the table because there's really nothing to say, maybe they match, maybe they don't, but it is peculiar that, the program is giving you G values of 1.7, which are frankly completely nuts for this kind of system. And then the ones that are all around 2 or a little more are pretty much okay. Okay, and then the last thing that I want to mention, which is probably the most interesting aspect, although really getting out of my knowledge base. And as I've said to Dan and Mihail, that they're in the top, I didn't even say 1%, well, I don't say part per million. There's probably certainly not a million people that know it, but there's a small group of people who are experts in the Jan-Teller effect. And in fact, I think it might even be today or the next few days, they're having their conference, which I just have to say, another sad thing about COVID, I've never attended it. I but they've had it in really cool places. They had one in Tartu, Estonia, and in, forget the name of the place, but in Spain, on the north part of Spain. I've never been to, on the north coast, yeah, near Bilbao. I can't remember the name of the place, but very scenic based on the pictures, an interesting area. They were even going to have it in the United States, believe it or not. Well, this was in the previous time, but that was supposed to be, I think, 2020, and that was canceled. And then another sad note, the organizer was John Stanton at the University of Texas, Austin, that I just learned about from this conference, that he died suddenly. And so that's a real loss for people in computational chemistry. I didn't know him personally, although I knew somebody that had a class from him actually, and he was a really good teacher in addition to researcher. Anyway, so now they're doing this conference online, and it's run by somebody at York University in Toronto. And so it's all online, and it doesn't sound like they're going to in person. So no potential trips to Tartu or Spain or whatever. Anyway, but so those people that attend that meeting are the world's experts on the Jan-Teller effect, and I'm certainly not one of them. But this is just a simple, I won't say general chemistry, but let's say, inorganic junior level in US gradations in organic chemistry, picture of what's happening. So this is the high spin. Um, Actually, this picture is, this is not, am I screwed up here? Okay, well, anyway, uh, that's okay. This is a picture of a Jan Teller effect. It's not really what the one we're talking about here. But in any case, you can see what happens. This is the tetrahedral symmetry. And then we go to C3V and you get this orbital splitting pattern over here. And then the key thing in terms of the Jan Teller effect is that you have a degenerate, orbitally degenerate ground state. So these, in this trigonal symmetry, these are very mixed. So it's xy and x squared minus y squared, but then it's mixed with xz and yz, and these are sort of the major components in this case. And the Jan Teller effect is one that leads to a splitting here, so that we have a net lowering in energy and a reduction from the in symmetry from this orbitally degenerate state. So anyway, and then the way that is effected is by vibrational coupling. So the vibrational modes and the electronic mode. And like I said, this is correct, but this is not a quintet. So I'm not sure what I was doing in putting the electrons in there. I got to fix that. But anyway, it's like I said, this is valid, but it's not the right spin state. Anyway, so these are the kind of vibrations that you can have. So we have this, forgetting about all the fancy scorpionate ligand, we just have these 3 nitrogens, we have the iron, and we have the ancillary ligand. And it's what's going on in this trigonal, ideally trigonally symmetric environment, that this coupling of these vibrations here, both the stretching positive and negative. This is where the optimization, the plus and minus, is related to this. And then the bending modes over here. And so it's that coupling of vibrations with electronic transitions that gives you this orbital splitting. And that's, to my simple-minded view, is one of the things that makes the Jan Teller effect so challenging, is that we're kind of going away from the Frank Condon model of, the stuff isn't moving around. We got the electronic transitions, we got the vibrations, and we're not really treating them together. And yet you have to, otherwise this can't happen. So this is the what was used in the calculations. Anyway, so the upshot of it is, yeah, I don't know why I have that. That's just the same figure again. Okay, well, that's what happens when you do this the first time. Anyway, so the upshot of it is, though, that they can do all these calculations of the orbital energies, and that's what's shown here. So this is not actually the Jan Teller effect picture specifically, but it's showing labels here that are still in the trigonal symmetry. But the important thing is that you can see the changes going from the fluoride, chloride, bromide, and iodine. And this is using the 2 different optimization models for the fluoride. So you can see that's, not much of a difference, but a little bit of a difference. But what you can see from this clearly, though, is, and you can say it's a lot of work for something that maybe is obvious from just general chemistry, but that there's a big change going from fluoride to the other 3. So that's not a spin orbit coupling thing, because there would be a big change in going from fluoride and chloride then to bromide and iodide. But here, fluoride, the really hard ion, seeing the hard and soft model, is completely different from the other 3. And the other 3, while not the same, are relatively modest in terms of the orbital energies. Although the thing about it is that because there's so many different contributions, and particularly in a case such as this one, to the zero field splitting, that the trade-offs that occur here can lead to fairly different values for the zero field splitting in each case. And so that's what's shown here. And it's that's something to take forever to go through all the numbers. But the point is, you got the 2 different color codes for positive and negative, and you've got the D and E So you want to compare parentheses to each other. That'll give you your E, and then the non-parentheses to each other. That'll give you the D, and they're just kind of all over the place. So it's really, the bottom line is it's almost impossible to be able to say, oh yeah, you have this kind of geometry and you have this kind of ligand and you're going to get this kind of zero field splitting. There's just too many factors. And then the more graphic view of this, I don't say yelled at Dan, but I criticized Dan. I said, Dan, you got to make these bigger. I blew this up like crazy. And there's so much empty space that he could make these little guys a little bit bigger, and we would have more to see and not so much white space. But anyway, so this is what they look like. And as I said, I tried blowing these up quite a bit, and it's still really hard to see, and you can see the resolution isn't so hot in this expanded scale. But anyway, enough criticizing. Dan has done an enormous amount of work for this. So you can kind of see what these orbitals look like. This is clearly the z-squared over here. And this is, you can see is sort of like kind of an xy, x squared minus y squared. And these are, the coordinate system isn't so clear cut, but it is kind of like what you'd expect in these cases. And then the last thing here, I don't know if okay, yeah, we'll get to the questions in a second. I'm almost done here. So I talked about a refugee, Jerry Trofimenko. Here's another one. That's his Hungarian name. They have last names first in Hungarian. I go to Wikipedia, all kinds of cool stuff, go down a big rabbit hole there, but this is his Hungarian passport. What's kind of cool about this, it kind of shows how things have changed in that it's in Hungarian, obviously, but then it's in French, because that was the diplomatic language back in 1935 when this was issued. So French is not so, maybe I hope I'm not upsetting anybody, but it's not as important now as it was 90 years ago. And that's just the way it goes. Anyway, so yeah, that's the old Kingdom of Hungary, which was officially what it was at that time still. Anyway, so these are the cool pictures that people who do the on-teller effect show, and it's this idea of this trigonal vibration. So these are these vibrational modes that we're talking about and looking at the energy as basically this thing is doing its vibration. What you really would need is a movie, I think, that would kind of show this. So, and then, but I don't have that. So this is the potential energy surface. This is just looking down the top here with different energies. And then this is a section here, which is at along the Q theta, this bend axis over here. And, people call this, I guess, I don't know if this is really the Mexican hat, and that's not really a kind of sort of, some people think that's kind of offensive, but whatever, it's this kind of shape here. So these are kind of cool pictures, which I like, although I'm not the right person to describe them. So yes, another refugee, Edward, Eddie, whatever. And they can do all kinds of really fancy calculations as well. So here's I think almost the last slide, possibly, showing a whole bunch of numbers here, which I've tried to kind of get information exactly what they are. These are the energies of these bends, and you can see they're really, really tiny. So it's remarkable to me that they would have any effect, but you'd have to ask Mikhail Atanasov about that sort of thing. And then there's these energy, well, these aren't really energies, these are energies normalized for the very small vibrations that are involved. So if you think about it, the energy is small, but the distortion is small. So you have a small number divided by a small number, you can actually get a pretty big number. So these are not in wave numbers, wave numbers per angstrom. I don't have a good feel for that, or certainly per angstrom squared, but yeah, that's what they are. And you can at least compare among the different complexes. The last thing, which is, oh yeah, this is James Franck. So he was another refugee, a two-time Iron Cross winner in the First World War, which didn't do him too much good or any good in the regime that eventually tragically took over. But anyway, so here's the energy of this. And this to me, at least, is sort of the bottom line that matters, because I had that little picture with the wrong orbital occupancy, but nevertheless showing the energy splitting. And this is the kind of numbers that you're getting. And, it does depend quite a bit, as we saw with the other parameters, on the geometry, which that perhaps should not be a surprise, but these optimizations, maybe you need to have a really optimal optimization. I don't know. I don't know what that really means, but it's quite a big difference here between the H only, that's essentially the crystal structure, and then what's coming from the optimization. You can see, at least in this case here, the bromide and the iodide, it's pretty similar in terms of the differences. And I personally think that this number here, the larger number, is probably more realistic. So, go figure is all I can say. And in this case here, the crystal structure that we had trigonal symmetry, so it was not possible to, in theory, then there'd be no effect like this, which is probably not realistic, but that's just what we're stuck with the crystallography. And then here with the fluoride, though, it seems to work out reasonably well. So that's the story on that. As I said, I'm not the person for the real hardcore Jan Teller effect. If anybody's interested, I can give you a link to the conference, which, as I said, I think is going on now on Zoom, and they have people from all over the world, so they have some pretty crazy times and that sort of thing, although it's coming out of North America. Anyway, so just some conclusions is that high spin iron 2 is a pretty good or pretty important system. You can talk about all the biological relevance, which I could go on and on about, but I won't. But the techniques in Tallahassee, also used elsewhere, the high field EPR, that is to say the field domain and the frequency domain firms, are both good techniques. But don't forget, just go fire up your plain old EPR spectrometer, and you might see something from high spin iron 2, also manganese 3. There's all these S=2 systems, which are not numerous, but they all in principle could show something. But probably, if you really want to look at iron, Mossbauer is the best, if with the caveat that zero field Mossbauer isn't going to tell you anything except some sample purity, and then, oh gee, it's high spin iron 2, which hopefully you can figure out from just the chemistry that you've done. But the field dependent Milheim style Mossbauer is really a good method, given that with the other few places where it's available. And maybe there's a trend, but it's not an obvious one, and it really requires some very serious calculations to be able to extract anything quantitative from it. And then this particular system, we kind of I thought, oh, this is a pretty nice one to look at, shouldn't be too bad. But because it has the Jan Teller, if this is the correct orbital occupancy, which I should have had in my diagrams, I got to fix. But anyway, yeah, I had paired it when I shouldn't have. Anyway, but it's interesting because it's an unusual case of the Jan Teller effect. That is to say, not unusual in the sense of the effect, but it's unusual in terms of the system in which it occurs. That these three down here are probably the cases where, I'm not going to say 90%, but whatever, some number of people that do look at the Jan Teller effect in transition metals, because as you can learn from the conference I'm referring to frequently, there's all kinds of other weird, to me, situations. It's a weird being anything not with a transition metal. For example, the nitrate radical, so not NO3 minus, but NO3 dot. You think about that's another trigonal system, right? And that's a one that seems like there's a couple talks on. That's an interesting Teller effect case. But the high spin D, I just put in chromium, but it's the high spin D4, the low spin D7, and the just S equals 1/2, the D9. These are the biggies, and copper 2 is beloved because it's so so easy to deal with. Chromium 2 and even manganese 3 not as much, and with cobalt you got to get a low spin system. But so those are all pretty popular. But now I don't say we're the first, but I suspect in this study, thanks to Dan and Mihail, this is, I'm sure, the most thorough study of the Teller effect in a tetrahedral, this E3T, it's a similar kind of system, but one in a tetrahedral symmetry. So that's it. I don't know how we probably went too long. I apologize for that, but I'll thank everybody for hanging out on Zoom and handle any questions if there are any. I don't know, Thomas, how you want
All
to
right.
go with
Thank
that.
you, Josh, for this extensive seminar. Yes, we already have some questions from Amrit actually. He wrote it in the chat, so
Okay.
you can see that. I would start reading the third one because it connects with a question that I have. So the question from Amrit is, do you have any recommendation on what type of resonator or probe would be optimal to look at this kind of high spin metal in a CW? I guess it's X-band.
Yeah, right. So so Mike Hendrich at Carnegie Mellon, he's really pioneered the use of the parallel mode detection, and that is better. I mean, I don't know if you have, I think with I'm sure it's possible with Easy Spin. I don't use that. I use Andrew Ozorowski's spin program, but his program, I'm sure with Easy Spin, you can just kind of do an in silico, if you want to call it, experiment where you could put in S equals 2 and some small rhombic splitting and just click or whatever you select between perpendicular and parallel and see the difference. And it should be a lot better with parallel. But if you don't have that, don't say, you don't want to go the way, oh, I can't do parallel mode. Why should I bother? I mean, you might not see anything, but it's, as I said, I was using a regular EPR spectrometer X-band and still saw a quite strong signal. I mean, it's pretty high concentration, but the thing is just to look at the low, go to zero field. There was one, it's not really a resonator thing, but one thing that they did in the Hoffman group that was pretty cool, which they don't have set up anymore, but that was to take, they have an immersion Dewar. I mean, I don't have any pictures, but it has a tail, right? And then, normally you have the wand. Well, you have the one going down with the cavity in there, and then you have just, you'd all know your regular Bricker, Varian, whatever kind of huge magnet that is going perpendicular, but they had a coil of wire with just hooked up to a DC power supply, and they fit it over the tail. And so now the field is going, in the parallel direction. So if you have that kind of setup, and I could connect you with Pete Doan at Northwestern, who could give more details on it. So it's possible not to change the resonator, but if you can move out your Dewar configuration, like I said, this is possible. I don't think it really would be feasible with a flow cryostat, but with this Janus Dewar with the tail, they could just make it like a, freshman physics kind of setup of here's a coil of wire with the current going through it. And I don't know about how they calibrated it. I think you could put a Hall probe in there, something. I'm not really sure. And, it's not even that the field, I don't remember how it was calibrated, but you could actually do a parallel mode that way with the magnet rather than with the resonator. But if it's probably a good idea to get a dual mode if you have the money and are sort of starting from scratch, but it's not required. So let's see the second part. The DFT. Yeah, that's, I mean, you know, I guess, I don't know, when I say comment on why this, I mean, I guess it's sort of, I don't want to say cancellation of errors, but if you just think about it, it's, I mean, the different, I mean, these are pretty small effects. And, I would kind of like just comparing the average G value just because, well, I guess you could say just because it works better, but I mean, you're kind of, the components are just not that critical or that easy to correlate with anything, but it's okay, we get 2.2 and we calculated 2.2 and that's nice, and just kind of leave it at that. So, I mean, I'd say comment on why it's the case. I guess it's just because, you're just averaging out some variations. I mean, something's going to be low, something's going to be high. And I don't think that there's, I guess the thing is, and people who know a lot more about the calculations can and tell me better, but I don't think there's any systematic error. I mean, it's, there's so many contributions, and, you just get a bunch of things and everything kind of lumps together and hopefully can get relatively close to experiment. But the individual components, it's, I mean, if there's a huge difference, uh, maybe it can detect that, like say, maybe, a porphyrin really axial system, something like that. I don't know, but yeah, it's sort of, who cares about that? Okay. Yeah, so I guess have a meeting. So then the last thing,
And
that the DFT functional, yeah, so uh there's a general, boy, I don't know. I mean, yeah, so these were the zero field splitting. I have it in the slide. I don't remember now what it is. I mean, I could go look at it, but yeah, it was nothing too unusual. As far as general, what I would recommend, I don't know. There's just so many out there, and I would probably, I mean, it's sort of a cop out, but that's something that the Orca Forum probably deals with and probably addressed there, where there's a whole lot of people that know a lot more about that. As you could see, though, that the thing is, I guess the last thing I'd have to say is, though, that, in the computational thing, people think, oh, I got to try this different functional or whatever. But the geometry was so critical too. And that's, so that's the whole nother parameter space. And that's a big problem because, should we try and include solvation? Are we looking, we're looking at solids. The X-band EPR that I did was in toluene solution. So that's pretty, low dielectric kind of situation. But there's all that sort of experimentally connected things that have nothing to do with the functional that you use. So it's really hard to say. Yeah.
okay, thanks.
All
If
right.
are there other questions from the audience? You can, if you have any question, you can unmute and
Yeah.
ask directly.
Yeah, that's right. I mean, anybody has any other thoughts, just,
Yeah.
guys.
I have actually a question, still going back to the X-band EPR. So you said that, yeah, you can see something, spin equal 2 maybe, but what information can you extract? Because the spectrum you showed was like a
Oh, yeah.
large blob.
Yeah.
And how
Yes.
critical is this information that you can
Well, it
get?
kind of depends who you ask. I mean, Mike Hendrich does really exact simulations with God knows what kind of line shape things where they match it really closely and they get all sorts of stuff out of it. I mean, the problem is there's the thing that you're ideally getting is the rhombic, the E component, um, where you're assuming that the D is relatively, or the E over D, I guess, is what you're getting. So in theory, you can get that. And I did find when I was sort of fooling around with that, that the shape is hard to get, but kind of the crossover, which you could say, okay, that's the observed G value, is relatively sensitive if you say, okay, let's keep the intrinsic G value the same because that's going to change, it all goes into the same equation. So if you say, okay, let's just say it's a G of 2.2 and leave it at that, and then vary E and it'll move around. And so with that, then you could say, okay, well, based on this model, that's what it is. But if you start saying, well, what about if there's some cubic zero field splitting, the B4, 0, B4, 4, whatever those various parameters are, then, as I said, this is the kind of thing that's nice using, say, EasySpan or Andrew's program where, you just can sort of fool around and see how things change. Like I said, the detection mode or the parameters and so on. And, by
Okay.
itself, it's not that great, but it is nice. And the qualitative thing in this case was it was clear that for the fluoride, we could see it, and that has the small rhombicity. And for the other three, we couldn't, and those have the large rhombicity. So, that's a kind of nice aspect, at least qualitatively.
Okay. Thank you.
Alrighty. Oh,
If there are no further questions, yeah, I would thank Josh again for this nice seminar.
thanks.
And yeah, and
Okay. Thank you all for sticking around. Good luck,
yeah,
everybody. Bye. Okay,
thank you. Bye bye.
bye.